Can you hear me without the microphone?
Sure.
Yeah.
Not easy.
Yeah, okay.
It's a bit noisy.
So. But then it's too loud. Huh?
They could go.
Why do you go in the first row?
Yeah.
I feel.
The air conditioning has this ambient noise.
Yeah, but if you go to the first row, then you can hear me crystal clear.
And to sit in the first row.
Oh, shut up! We are waiting since 5 minutes for you. Yeah. In the first row. Seriously, it's not loud enough. I grabbed the microphone. Yeah. Okay. We announced the talk on it from Rubik, black holes and wormholes and entanglement, and I changed it because I realized that I gave the talk 2 years ago. Although a lot changed in physics in the meantime, I decided to give something that is absolutely hot now. It's post-quantum cryptography. A lot of political stuff happened in the last 2-3 weeks. Right? I decided to do this, and then I decided to discuss, because we also have a data day, in the second part I discussed topological data analysis, because I'm always glad to chat with Bernard about data, and there are also a lot of quantum aspects that I will also highlight. So we begin at quantum computing, post-quantum cryptography, and I'm also speaking the role of, I work for a company called WSO2, and we are doing a lot in this area. We're enabling all the products to become quantum safe. And this is why I can give you some experience of what is currently happening, and what effort it is, what the downside and upside are. And if you want to read the boring details, this is 60 pages that Johanna and I have written. It's a lot of mathematics. You will enjoy. I hope so. Yeah? Yeah, okay.
Now I have to go fast.
Huh?
He wants to leave now. Oh, what is this?
Yeah, this is
The paper.
I always use the wrong button. So, for the first hour, I'm going to discuss fundamental phenomena, because typically we introduce we have a tutorial session at the very beginning, and I use the first 20 minutes to introduce quantum phenomena and a little bit of quantum algorithms. Then I point out what are the threats that quantum computers, besides the good, nice things, bring to the table, what is the rescue, and then I'm closing, as usual, very nicely. So, fundamental phenomena. As we all heard, the quantum, by the way, you get all the slides. If you want, you get all the slides. Absolutely, yeah. The quantum world, Werner Heisenberg, Nobel Prize laureate, was one of the first who worked deep in the theory of quantum world, is completely different from the classical world, fundamentally different, because the quantum is not deterministic at all. In the contrast, it is completely stochastic. That means especially that the result of a measurement, you have an experiment and you measure, it is not known in advance. For example, you know S equals 1/2 gt squared. You can measure how fast you are when you fall. You can immediately know, if I measure here, this is the current height of the ground. But this is not true in the quantum world. If you measure, you can't predict what is the outcome. This is what Albert Einstein said. It's unbelievable. It can't be. It can't be. I don't know. It's a realistic theory. You know everything in advance, even if you take a look at it. Einstein said, the moon is there even if I don't look at it. But it was completely different. And looking at the moon is a measurement, and you know it is there. Right? But here in the quantum world is very different. It means only the probability of the result of a measurement can be computed upfront. And so what happens before the measurement, cannot be said with certainty. And this is, as I said before, by Einstein. By the way, he got a Nobel Prize for quantum physics as the inventor of quantum physics, not for the general relativity that many people know. So he got this Nobel Prize for quantum physics. And he said, there is something wrong. We will see what happened in the course of the history. And this is nicely illustrated by Schrödinger's cat, our famous Nobel Prize winner from Austria, this is Erwin Schrödinger. He invented a thought experiment. He put some radioactive material there, and the radioactive material is known to decay completely stochastically. And if a material decays, there is a sensor that detects the decay. There is a leverage. The leverage, there is a hammer, mounted, and if the decay happens, the sensor gets aware of it, the leverage is released, the hammer falls, and then you have here a bottle of poison, right? And if the hammer destructs the bottle, then you will die. Who will die? This is a cat. So Schrödinger's experiment says, I put a very nice cat, you see a lot of cats down on the road, I put it into the box, and then I close the box. So what is the state of the cat when you close the box? You don't know. Because the very second when you close the box, the matter may decay, and then this happens and the cat is dead. Or because it's completely random, but the decay may happen in 15 minutes, 30 minutes, and the cat is alive. So from the outside, the cat is both dead and alive. It's a zombie cat. You don't know what the state of the cat is. That means it's dead and alive, and there's some crazy notation here. We write it this way, I don't explain what this is, because the cat is in superposition of being dead and alive. Superposition is a key word, you all have heard about it. So, and this is now the origin of quantum computing, because a quantum bit can be in state true and false at the very same time. Right, at the very same time. We say the qubits in superposition of 1 and 0, and very precisely there's this equation, the qubit q is in state 0 and 1, and here you have some coefficients, alpha and beta, that form a linear combination of true and false. So what you can write it, here is on the x-axis you have false, on the y-axis you have true, these are the base vectors, and you have a linear combination here. And then there's the so-called Born rule. The Born rule says that this coefficient determines the likelihood, the probability, whether when you measure true or false. That means alpha is the probability, very precisely, it's the modulus of alpha square. This probability of measuring 0, modulus of beta square is probability of measuring 1. And because you will measure either 0 or 1, they sum up to 1. Right? So the total probability, with 100% you measure something, right? That means modulus alpha square plus modulus beta square is 1. That means this is really a unit vector. The qubit represents a unit vector. And I was cheating here a little bit. I have drawn a two-dimensional plane here with a one-dimensional circle, but in fact it's a bit more complicated because these alphas and betas are complex numbers. It has to do. You are late, you come here. You want to? So these are complex numbers. It has to do with quantum mechanics. These are waves and so on, and waves can be best described by sine and by trigonometric functions. So these are complex numbers. That means that the qubit lives in a four-dimensional world, right? These are basis vectors in C2. These are complex numbers. It lives in a four-dimensional world. But luckily, we cannot imagine what four-dimensional things are, except you are mentally insane. You can use polar coordinates, and if you use polar coordinates, then you represent a qubit in something called the Bloch sphere. Bloch is yet another Nobel Prize laureate. He basically invented this possibility to rewrite it, and then what you get is the Bloch sphere is the surface of a three-dimensional ball in three-dimensional space. So a qubit is something that lives on the surface of a three-dimensional ball. This is not what we can imagine, that we are used to it. So this is fine. And this already gives an indication what the power of a qubit is. So the classical bit is either true or false. There is no combination. Classical bit is either true or false. Right? So two possible values. A qubit is something that lives on this Bloch sphere, and you have an infinitely many possible values. So a qubit already has many more potential, many more possibilities, because it's any point on this Bloch sphere is the value of a qubit, while here you have either 0 or 1. This gives us a first indication why a qubit is so powerful. Next is, in classical computing, we bundle bits into a register, and now we do the very same with a quantum bit. We bundle the qubits into a quantum register. That means here we take n qubits, and now while a qubit is in superposition of 0 and 1, here we have 2 to the power of n combinations of 0 and 1s. Right? That means all can be 0, or all can be 1, the first one can be 1, and so on. So we have 2 to the power of n possible values, and the quantum register is in a state of 2 to the power of n potential values. Right? And n, this is exponential. That means the quantum register is in an exponential number of state, and we know from astrophysics that the number of atoms in the universe is less than the power 10 to the power of 90. If you rewrite it, 10 to the power of 3 to the power of it is 2 to the power of 300. That means if you have 300 qubits, you have more information in your quantum register as we have atoms in the universe. If you want, this is why you can't simulate a quantum computer or a realistic quantum computer, because if you want to mimic in Jülich, they have the largest GPU cluster for simulating quantum. They have 5,000 GPUs, and they only can simulate 45 qubits. And if you want to simulate 46 qubits, you need to double the number of GPUs. That means 2 to the power of 50 can't be simulated. 2 to the power of 300 means we need to turn each and every atom in the universe into a cell of a classical computer just to simulate it. Well, this can't be done. And what we are doing is we are working in Stuttgart with 400 qubits IBM machines, and you can't simulate it. What you are doing is far beyond any realism to simulate. So, and all these values are manipulated on a quantum computer in a single step. Quantum algorithm manipulates all these things in a single step. Each atom of the universe is manipulated in each step what the quantum algorithm does. This gives you already a second impression. These must be very, very powerful. So, this is called quantum parallelism. All these HPC computers, they are ridiculous compared to what the quantum computer can do, that you can access 400 qubits on my IBM machine. Simple. But the real miracle comes now. So, if you have 2 qubits, what you can do is you can relate them, right? This is called entanglement. Right? There is some correlation between the 2 qubits, And if you fiddle around with 1 qubit, the other qubit is also manipulated the same way. So if this is threatening, this is threatening too. So what you do is, you can put an analogy, you take 2 dice, and then, because I'm old, I stay on Earth with my black dice, and you fly to Andromeda Galaxy, 1.9 billion kilometers away, and once you arrive there, I hope I'm still alive, right? I throw my dice, and once I see the result, I immediately know what the space of your dice is in Andromeda Galaxy. Immediately. Immediately means, oh, I need to go back, sorry, So immediately, while the animations are running, immediately means without any time delay, or a delay that we can't measure, right? And this was another argument for Einstein that quantum physics must be wrong, or we must miss something. The first thing, we must miss something, because this experiment is also a thought experiment that was invented by Albert Einstein, right? He invented the so-called EPR, the entanglement, by papers from Einstein, Podolsky, Rosen, EPR in 1935. They came up with a thought experiment and mathematically proved it, that entanglement is possible, but there was no chance to do that in experiments, and it took until 2017, right, where Anton Zeilinger did the measurement, and they got the Nobel Prize that nearly 100 years later they had rock-solid experiments to prove that entanglement can be measured. And this is absolutely strange. Einstein always thought this is now the final kiss of death to quantum mechanics, but the contrary, right? Because this is the real power behind quantum computers. And what I wanted to talk about, and I skipped it only, is that Einstein, Podolsky, Rosen entanglement was brought together with a paper that Einstein wrote with Rosen on wormholes in space. So what today's physicists believe is, and they have a lot of, you can basically derive a lot of physics based on this assumption, that during entanglements, the qubit become nanoscopic black holes, And entanglement means that the two qubits build a so-called wormhole between black holes, and if one is on Earth, the other is in the Andromeda galaxy, there's a wormhole in space, and if you fiddle around with the first black hole, immediately through the wormhole, you get past this information to the other black hole.
That's the question. I always thought it is a symmetric relationship,
Yes, it is.
but you say mouth and bridge, so you give it a direction.
No, it's bidirectional.
Okay.
Absolutely bidirectional. So absolutely bidirectional. Right? This is a 2 to 3 hour talk which I skipped. But if you are curious, I will ask Juan Ma next year. He is managing the quantum session. Maybe he asked me to give them the talk. Okay. So, and the consequences of superposition, quantum parallelism, and entanglement means that you can build algorithms that are faster, much more precise, and other stuff that I skip over than classical algorithms. And the impact is that you can solve problems that cannot be solved at all or efficiently on a quantum computer, right? And that basically means, for most problems we have polynomial quantum algorithm that solve exponentially classical algorithms. And yeah, they can be solved in practice now. New business models do occur. And in the second part, I will jump into one algorithm, because what happens today is when the quantum algorithm guys invent a new, extremely fast algorithm, the classical computer scientists get jealous. They say, these damn quantum guys, they solved the problem that we didn't solve for the last decades, and they try to build a better algorithm. Sometimes they succeed. This is called dequantization. That basically means that quantum algorithm guys also try to prove that you can't dequantize a certain solution. I jump into that when I discuss topological data analysis. Wolfgang.
But I think undecidable problems remain undecidable.
Yes.
Okay.
Yes. So undecidable problems remain undecidable. Yes.
That's good.
Absolutely. Yes.
I'm happy.
So you're
Absolutely.
safe.
You are safe. You are safe. So now how are qubits manipulated? A qubit is a point on the Bloch sphere that means a vector of unit length, right? Meet the vector of unit length. And what you do is, if you manipulate it, you apply an operation, you turn a vector of unit length into another vector of unit length. In the linear algebra, these kind of maps are called unitary maps, length preserving algorithms. So, and a series of such unitary maps is again a unitary map. That means basically the quantum algorithm is nothing else than a unitary map. If you invent a new quantum algorithm, you think in linear algebra and you derive unitary maps. In fact, it's more complicated because the quantum physicists transform the problem into the Schrödinger equation. They solve the Schrödinger equation. The Schrödinger equation has a Hermitian matrix as the centerpiece who describes the evolution in time. This is the solution. And then the physicist is done. And then you go to a mathematician, because the exponential, the matrix exponential of Hermitian is a unitary matrix. They compute the exponential of a Hermitian matrix. And then they say this is the unitary. And then they come to the computer scientists and say, you poor guys, turn it into a quantum algorithm, because there's well known how to break a unitary matrix into a series of two-dimensional matrices and four-dimensional matrices. But it's a joint project that people are doing. So, and the quantum circuit is as follows. The quantum circuit can be expressed, as I indicated before, as a series of 1-qubit manipulations and a series of 2-qubit manipulations, because you need entanglement. And 2-qubit manipulations create entanglement, right? And many of 2 bits. And this is then called a quantum circuit, right? So quantum algorithms consist of circuits these days. That means the qubits are drawn as horizontal lines. The 1-qubit manipulations are the squared here, right? They manipulate here. Then you need the 2-qubit operations. C-knots are drawn as this way, and we abbreviate it as this is a unitary algorithm, right? And quantum physicists write down this unitary only, and then we computer scientists need to turn this into a quantum circuit. This is here a tool, several tools exist. We use often this IBM quantum composer. It's exactly what I showed before. Here are the qubits, and then you have here the palette of language elements that you can use in order to draw your quantum algorithm. Right? It's straightforward. Now you want to manipulate real data. Quantum computer is nice, and physicists think it's nice, but how do you solve real-world problems? Real-world problems are based on real-world data. How do you get real-world classical data into a quantum computer? Because the quantum computer is manipulating quantum states. That means we need to transform real data, classical data, into quantum data. And this is done by generating per data item, per record, per entry in the table, for example, a circuit. So you need to analyze the data, and based on the data to create a little circuit that runs and generates then a quantum state in the quantum computer. So if you have some personal data record, first name, last name, birth date, you need to transform it into this quantum beast here, right? And this is done by inspecting the data, and based on the data, you do something that's called state preparation to prepare the state that the quantum computer can manipulate. And then the quantum algorithm runs. Right? The quantum algorithm runs and produces results. So the result is yet another quantum state, but we want to say whether Frank gets a salary increase or not. Right? This is important to me. So we need to turn this quantum state into classical data. This is done by measurement. Each qubit is asked, are you 0 or are you 1? It's a random experiment, right? And then you get here a list of bit vectors. Let's say I get 0, 0, 0 out. Then I keep track how often I certain bit strings measure. In this case, I measured 0, 0, 0, 1. Then I let the quantum algorithm run again. It runs again, and the next, but an iteration is referred to as a shot, I get this bit string. So I keep note of this bit string, and then I iterate it hundreds of times, thousands of times, and then I get this distribution here, right? And in fact, then I can draw a line, and I get a probability distribution. That means a quantum algorithm is performed many times on the same set of data, and then you get a probability distribution out of it. And it is the art of an algorithm designer to know which shapes of distributions come out when I run an algorithm several times. So the solution is the distribution, and they describe, if you see this shape, the answer is yes. If you see the other shape, the answer is no. Right? So the result is the probability distribution, and the distribution is then post-process. I have to analyze the classical shapes in order to know what the results are. And this is invented by John von Leymann, computer scientist in London. This is one of very few people without a Nobel Prize. But he has severe impact on computer science, on mathematics, on physics. The whole thing has been described by John von Leymann. That means a quantum algorithm consists of classical parts and quantum parts. For example, the classical pre-processing part is I take a look at the data, generate a circuit that transforms the data into a quantum state. Then the algorithm proper runs, and then you perform the measurement on a QPU, and then you have classical post-processing in order to analyze the result, this probability distribution. So a quantum computer always needs to be padded with classical computers. Right? So you won't see a quantum mobile phone anytime soon because it doesn't make any sense. It's a special purpose device that solves particular problems extremely good. And this means that quantum algorithms are hybrid, right? Hybrid. And it's not as simple. Here we run in the project that we have real workflows, tons of workflows with tens of steps, and only one or two steps then went into a quantum computer, did some measurement, and then it's similar like if you buy SAP, and some people say bubble sort is an application. No, it is not. It's a poor algorithm, but it's not an application. And physicists say, oh, I have a new application, I have a quantum algorithm. No, it's only a micro piece of the overall solution.
what
You
extent?
need to speak up.
To what extent is it important that I already know the architecture of the QPU in this case? Like, is it,
Again, louder?
no, to what extent is it important that I already know the architecture of
The hardware.
The hardware of the
Extremely important.
Okay.
Several, so quantum computers can be built with various technologies. You can use it, you can build a photonic quantum computer, a quantum computer that consists out of superconducting devices, out of ions, out of Rydberg atoms. And it is the hardware that determines which kind of problems can be solved best. Each universal quantum computer can solve any problem. For example, if you have problems that require connections between each and any qubit, because you need a physical connection in order to entangle qubits, you prefer ion-trapped computers. Right? If you don't know that, you have superconducting computers.
But I was referring to the pre and post-processing.
No impact at all.
Okay, but this means I could schedule a task also on another machine base.
Absolutely, yes. Yes.
But you have to decide how many qubits you want to use. Right?
Absolutely.
And the mapping to the state has to be done. That state preparation.
You need
And
to
that
know number of
depends on
qubits.
the number of qubits.
Absolutely, yes.
Yeah.
But this is simple.
Yeah.
Right.
Does it mean that if there is one task, it will use the whole qubit cluster? Cannot be parallelism
Yes,
between the
you can
tasks?
split circuits into fragments. You can schedule them to various machines. You can say, okay, this sub-circuit is suited for an ion machine, the other is used for a neutral atom machine. You can do it, but you have an exponential overhead. The more often you split, the more effort you have to combine with classical mathematics the distributions again. Very good question. No, because you need to find out which hardware do I need. Do I need to split the circuit? Software engineering. Software engineering, not systems engineering. No. If you want to solve an overall system, you should find out when to use and then you have normal decisions how to split the quantum. Like you do yes, but is the software engineering is over? Is it actually no, because it's software engineering considering quantum. Quantum software engineering in this sense is normal, because it's software engineering and taking quantum. Thank you. So here I have a few quantum algorithms. What quantum computers do, for example, they compute eigenvalues. Yeah, very fast. Right? And an eigenvalue can be used for example, feature engineering. Right? And you will be surprised how many problems can be reduced in order to compute eigenvalues. So this is really a very nice workhorse. Then you can factorize numbers. We will see that in the second part of the presentation. You can perform molecule simulation in medicine. So we work with pharmaceutical companies together. They want to solve the individual medicine problem. They want to manufacture pharmaceuticals for your personal disease, right? Not for women and men together, independent of the age, so individual pharmaceutical. This is what you can use calculus for, and so on. The next would, for example, solving linear algebra, linear equations. Right? You can solve them, everything that you see here can be solved exponentially fast. This is only, there's a quantum zoo, quantum algorithm zoo, there's a web page where they have, in the meantime, about 100 algorithms that show how to solve most of the problems exponentially faster. So many problems can be solved there. For example, quantum machine learning, right? I assume that many of you know what support vector machines are. Support vector machines try to separate sets of data into groups. They do it by trying to find a hyperplane to separate numbers. But in this example, for example, to find the proper hyperplane. right? You can't draw a line here between the dots and the stars, but if you pump them up into a higher dimension by adding a third dimension, what is the distance from the origin, you go to a third dimension, then you can find a hyperplane to separate them. That means the trick is to blow up your problems into higher dimensions, and then you do that. In quantum, you have a lot of dimensions. With n qubits, you have 2 to the power of n dimensions. That means you can easily pump your data in extreme high dimensions and then separate the data. Right? And then you find linear separability, and you can determining this hyperplanes requires to build the scalar product of many vectors. Compute the scalar product is exponentially hard, but you can find a quantum algorithm that reduces computing scalar products on a quantum computer. It's called a quantum kernel, because you map computing much complicated. So, and it means to get both efficiency, you are much faster with support vectoring, and much more precise, because the support, the hyperplanes can be derived with much higher precision. Another interesting thing is training quantum neural nets. Most of you know the classical no-free lunch theorem in supervised learning. It basically says the more training data you have, the lower is the average error in learning a neural net. This is a fact. So the next thing in quantum, there's also a no-free lunch theorem. It basically says the more the training data is entangled, the less training data is needed to learn a quantum neural net. And in the extreme case, in high dimension, a single training record suffices to train a neural net with 100% precision. When I read it 5 or 6 years ago, my head was blowing apart. I said, this can't be, and I want to see experimental results. And I asked one of my guys, this is your PhD subject. He was shocked. He was absolutely shocked. Right? When he wrote a thesis, it is absolutely fine. He has his exams next Tuesday. Right? Next Tuesday. Absolutely fine. And we proved it. We got data from an automotive company close to Stuttgart. They have a quantum neural net to test before they deliver the car the Stoßdämpfer. Suspensions. These suspensions, right? They trained a neural net and they gave us a subset of it. We entangled it, sent it to a quantum neural net, and we learned it better what this automotive company trained the net with a single entanglement. So you can prove it. It has been published. So a lot of good things can be done, especially cracking keys. So this is not a good thing, but I'll explain you what happens. We all know that RSA is based on prime numbers, right? What you do is you need to take 2 large prime numbers, you multiply them. This is then the public key, and out of the public key you derive a secret key, right? It's a bit more complicated, right? Then you have your private key. And if the prime numbers of the public key, if the public key can be decomposed into its prime numbers, you can compute the private key out of it. Yeah, but again, deriving the prime numbers, this is a bit complicated. Factorization, prime factorization breaks RSA, right? But all known classical algorithms are exponential. There's no proof that we will not be able to find a non-exponential algorithm, but nobody found it since decades. And this is why we consider RSA as secure, because prime factorization is difficult. Even factorization, a number that is known to be composed out of 2 prime numbers. Right? This is surprisingly hard. Elliptic curves. What the hell is an elliptic curve? It's a curve like this, has this shape, and you can perform computations on an elliptic curve. For example, if you take 2 points on an elliptic curve, you take the line that connects the 2 points, it intersects the elliptic curve again, then you mirror it on the x-axis, and this is then the product of p times q. If you don't have a single point, if you only have a single point, you take the tangent, it intersects here, you mirror it, this is p squared. So you formulate elliptic equations based on this group structure. It forms a group, blah, 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 blah. And you also can then derive for the private key and the public key. And again, cracking private keys requires to solve these kind of elliptic curve equations. And all known classical algorithms are exponential hard. This is why we think elliptic curve cryptography is secure. And the elliptic curve cryptography has been invented after RSA because you have the algorithms are faster and you can have shorter key sizes. So ECC is considered to be secure. At the heart of elliptic curves and RSA, prime factorization, is something that is called discrete logarithms. You perform in number theory. If you introduce an exponential function, it's a discrete exponential function. You get only natural numbers, it's not a continuum. And if you compute then the reverse, the logarithm, you compute the discrete logarithm. Right? In quantum algorithms, there's a quantum algorithm that can compute discrete logarithms in polynomial time. This is Shor's algorithm. This is Peter Shor, the second non-Nobel Prize laureate in this presentation. And that basically means that the future quantum computer, not as of today, can crack today's cryptography that are based on RSA and elliptic curves and so on. Right? And it takes only days to minutes to crack RSA and hours to seconds to crack ECC. And if you add more qubits, I will mention that it takes a fraction of seconds to crack RSA. And the gory details, the method behind is, Johanna and I, this is also 70 papers, right? If you want to enjoy this one, it has to do with in-deep number theory. Right? So, public key infrastructure is everywhere. We use RSA and ECC and signatures and certificates everywhere in our digital infrastructure. If you establish a session with Amazon, with your online banking account, you use a TLS handshake. If you want to decrypt data, it's RSA or ECC or symmetric key. Symmetric encryption cannot be cracked via a quantum computer. You need to double the key size, and then you are as secure as you have the most powerful quantum computer. Right? So cracking symmetric keys can only be done quadratically faster. Well, so this is symmetric keys are fast. Digital signatures. You will be astonished how often in the world you use digital signatures. Everywhere. Cryptocurrencies. But I always say if you invest in cryptocurrency, you're a very poor guy, because it is already now known how many trillions of dollars will be lost. You can't expect to take the money out of the blockchain or somewhere else, but blockchains can be cracked very easily. There are groups that build new blockchains, cryptocurrencies, with post-quantum cryptography used upfront, but the existing cryptocurrencies, if they now would introduce post-quantum cryptography, the branches are lost. If you take a new branch with new crypto, trillions of dollars will be lost. So if you invest, wrap your money, and give 50% to me. And the rest is whatever you want to do with it. Secure messaging, certificate, blah, 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 blah. You know that cryptographic infrastructure is everywhere. And breaking this algorithm is a major hit of today's IT infrastructure. It has a serious impact on companies, government, life, online banking is gone, online chatting is gone, everything is gone. Yeah? But when is this powerful quantum computer available? Everybody's saying, okay, I can rest. Frank is a science fiction fan, right? This is the very far future. Okay, let's take a look. Today's quantum computers are error prone. We call it noisy, right? They show some errors. Yeah? Or they don't have enough qubits. They only have intermediate scale, which is referred to as NISQ, noisy intermediate scale quantum. It should, in analogy to RISC machines or KISS machines, right? They call it NISQ machines. But the technology is evolving very fast. I started to go from quantum about 10 years ago. Daimler was always paying me PhD students, and at one point in time, person reporting to CEO said, Frank, you need to work on quantum. And I said, Winfried, you are crazy. I don't do it. I said, you are a physicist and a mathematician and a professor in computer science, you need to work on it. I said, you pay, I do whatever you want. And after a couple of weeks, I was absolutely fascinated about these machines. Because I then built these machines, and I went to my former colleagues in the lab, and they said, yes, we are taking it absolutely serious. And then I got in touch with friends in the US that are building the J competitor, became IBM fellow, and they are always underestimating. They want to avoid hype. They are always underestimating what they deliver. And they said 10 years ago, in the year 25, we will 50 qubits, and then they had already 400. And it's nearly an exponential growth. And the machines, so noise is corrected very, very fast. In the past, people thought that an error-free qubit requires 10,000 physical qubits to protect them. In the meantime, we know it's 24, and they go down more and more. So error correction, noise reduction, the number of qubits is increasing fast. That means the expectation is that in a few years, quantum computers will be able to crack RSA, ECC. That means they will be able to destroy all of our cybersecurity infrastructure. Right? And such a computer is called a CRQC, cryptographically relevant quantum computer. So, and now comes the shock. Recent advancement, a few weeks ago, a paper has been published that showed how to use 10,000 atomic qubits, Windberg atoms. Here the hardware now comes again into the game, to crack to compute the discrete logarithms, and they needed about 10,000 noisy qubits, and 10,000 noisy qubits is a matter of very, very few years, right? And the execution time can be reduced by adding more and more. They have an algorithm, the more qubits you add, noisy qubits you add, the faster the algorithm gets. And this, many more advancements that don't show here, algorithmic advancements to speed up Shor's algorithm itself, right? A lot of advancements there. And the first reaction, a few weeks ago, came from Nature. Very serious journal. They say it's a real shock. Quantum breakthroughs pose imminent risk to cybersecurity. It was published in April, right? So it's about 2 months ago. Right? They saw the paper, even the Nature editor said this is a shock for all of us. And next reaction came from Google. They said quantum frontiers may be closer than appear, and they turn all of their infrastructure to become quantum safe by 29, in 3 years. Then, for example, Cloudflare, it's the infrastructure provider of all of our clouds that we are using. They turn everything to be quantum safe by 29. So this is what they expect, that in 3 years, all of today's security infrastructure is gone. 3 years. 3 years.
Is it enough? Is it enough?
No, do we see? No. No, it's even worse. So, why should you care today? So you should take away those many data that are secret and have to be kept secret for many years are encrypted with current methods. It means this data can be cracked in the foreseeable future.
If you have access.
Huh?
If you have access.
You will see, yes, if you have access. So it means encryption, and encryption based on quantum technology requires new hardware. So there is another stream in quantum computing. They invent secure communication mechanism based on quantum technology. There's something that is called the no-cloning theorem. You can't copy quantum data. That means you can't steal them, you can't observe them, but it requires a lot of completely new hardware. You need geostationary satellites. You communicate via laser beams from the satellite, from the town here. Chinese people are building it between the major cities. It is pure quantum technology, but yeah, it's also but because it's so expensive, the people say no, we can't build it worldwide. Right? We can't build it. It's interesting, and this famous algorithm BB84 got a Turing Award this year. The people who invented this algorithm got the Turing Award before this. But we need quantum safe procedures. Software that implements quantum safe procedures that I will discuss in the next minute. This needs to require all of the software in the infrastructure. We need to implement completely new encryption algorithm and need to inject it in everywhere in our infrastructure. Right? This takes many years. But people compare it, the year 2K, some of us are old enough, there was the year 2K problem, it is peanuts against what we have to do in order to change all of our infrastructure. You will see a few numbers a few minutes. So, and what happens if you have it? There's a phenomenon that people observe these days: harvest now, decrypt later, or steal now, decrypt later. Adversaries are getting data out of the internet. They observe communications going on. They take the data, store it, and if they have access to a cryptographic relevant quantum, they decrypt it and threaten you and say, I publish your health data, your financial data, the phone number of your girlfriend, right? And then you need to pay it. Yeah? This is seriously happening. Harvest now, decrypt later. So what about trust? Harvest now, decrypt later, addresses confidentiality of data. But what about integrity and non-repudiation of data, right? You sign something, you want to make sure that the message is not filled around with. And in today's world, trust is established in many signature certificates. Somebody discussed, I'm not sure whether this was Albrecht who left already, what identity of agents. Agents need an identity. Absolutely severe problem. I've worked for this company, there was too. Agents, you need to create identities on a second basis. Thousands of agents that are running around because you only want to grant access to data for one single transaction only, and they must be absolutely secure. And the signatures are based on RSA and EC, and you can crack them, fiddle around with the data very soon. And this is called trust now, forge later. This is what people are already also doing, right? They steal messages and documents and basically say, okay, I changed it, I changed the text and changed the signature accordingly. Well, the question is how much time do you have? A very simple inequality called Moscow's inequality. So the collapse time is the time you believe that a quantum cryptographically quantum computer will be available. Then the migration time is the number of years you need to realize a quantum safe solution. You need to change all your internal application, but because there's a whole supply chain you depend on, right? You need to also be sure that the vendors you use change their infrastructure. So, and then there's the shelf time. This is the time, the number of years the information you have must be kept secret. And if the migration time and the plus shelf time is greater than the collapse time, you are in severe trouble. Yeah, because then people can track your data. And, okay. And the time you have for migration is collapse time minus shelf time. So let's assume that you need to keep your data 10 years secret. The collapse time is 10 years. Then you have 0 years left to move your infrastructure. But we heard before, it's not 10 years, it is 3 years. You are already in deep shit without knowing it. Right? You are in deep shit. I guess this talk to a lot of CEO groups, and they say, oh, I'm in deep shit.
No, but still, they have to get access. If you don't have access for your shelf data...
Yeah, but people are stealing it already. They break into infrastructure, steal data, or they monitor traffic that's going, your health data is transferred from one doctor to another doctor. Secret data all about.
Yeah, this is what I'm thinking. It's going back from decentralized to centralized.
Okay, yes, if everything would be centralized, would be good.
Yeah.
My pension and IBM race.
Exactly.
Yeah, absolutely.
Exactly. The mainframe gets.
Yeah, absolutely.
Yeah.
So, collapse time these days is. So, when I began, it was 30 years. Then somebody spoke 20 years, 10 years. Now it's 3 years. Right? It's getting very, very fast. Biden came up with legislation recently, June, a couple of days ago. Trump also put out a new law securing the nation against advanced cryptographic attacks. Right? By law, the whole infrastructure of the US must be turned into quantum safe things until December 30. Right? Everything in the US must be transformed to become quantum safe. Blah, 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 what it means. They released a document how to do it. Right? Why do they have it? Well, this is currently being updated. The timeline they released last year, they say they're currently updating it. It was 30, 33. They say, oh no, we shift that to the left. to make it fast. There is a crypto task force. I picked out the financial infrastructure framework. It's about a year old. Right? They say that this cryptographic, they could break the fundamental security that protects trillions of dollars in assets, leading to systematic risk, catastrophic investment losses, and complete erosion of market confidence. Right? This is 2008, this crisis is nothing against it.
Yeah.
What they say, I need to read it. This is what they call the Q-Day. So it's waiting for certainty about Q-Day is a fatally flawed strategy. You should not wait, you should act now. Right? Because otherwise you will run into trouble. And they recommend to the banks, so if you start it in 25, you spend 10 to 20 million. This was the cost for an average bank. You need to 10 to 20 million investment to change your bank infrastructure. If you are reactive, if you do it in 2030, you need to invest up to 100 million or more. And if you wait for the Q-Day, you lose up to $1 billion. You lose. You don't. There's no reason to invest anymore. You just lose $1 billion or more. It's a severe threat that nobody realizes. Only few people realize in industry. EU is acting too. I skip over that, right? And there's a very famous legislation called NIS2. It's called Coordinated Implementation Roadmap for the Transition. This is not the important thing. The important thing comes now. This legislation, in the US and Europe, has impact on CXOs. So because CXOs are personally liable when the company they are heading is losing money. Personally liable. Right? So here, for take-wise, this is from the document. It's an EU document. There are always the links.
Well, but it says NIS2 directive introduces new personal liability,
Yes.
so they changed it.
Yes, because otherwise
to put more pressure on.
And the pressure is as follows: if I give this talk to CXOs, they get nervous. Oh, I'm already in deep shit. What Frank is saying, and then NIS2. Oh, I'm personally liable. Then the people turn around and say, oh, I have an insurance company. I'm insured. If I make bullshit, right, the insurance company jumps in, pays the money. No, the legislation said insurance companies must not repay the money. They are personally liable. Personal. Out of them, they get even more nervous. You see that they're nervous, want to grab their cellular phone, and then they say, okay, then I sell my nice house, pay the company the money that they lost, and then I jump to the next management job. No, the legislation says you will never be allowed to be a manager again in Europe or the US. Then they can go to China, but not in the Western world. Right? So, okay, blah, blah, blah. NIST, this National Institute of Standards, these are the old numbers. They are currently adopting it to 29. But if you communicate with a company in the US, you are they depreciate elliptic curve and RSA after 23, and after 35 it's disallowed. And the numbers are moved more closer to today. What is the rescue? The rescue in 10 minutes. Rescue in 10 minutes is lattice-based cryptography. So a lattice is a set of discrete points in a vector space, and they have a group structure. You can compute with the points here. And they have a basis. On the basis of the lattice, each of the green dots is a linear combination of the two red vectors. But there are several bases. There's also the blue basis. It's a bad basis. You can measure what bad means. If the vectors have a very different length and the angles are very close, very narrow, right? The computation are exponential. So what you use is, so to speak, your public key is the red one, the private key is the red basis, and your private key is the blue basis. Very complicated to compute, to decrypt data. So you compute a message, you decrypt it to the red dot because you use the red basis. And then in order to decrypt it, you need to find the closest point here. And this is very hard if you use the blue basis, right? And so this is very hard. All known algorithms classical and quantum are exponential. This is why we believe that these kinds of algorithms are safe. Right? They are, okay, so that's good. And this is why the NIST kicked off something that's called the Post-Quantum Cryptography Task Force 2016. They did it already 2016. They built algorithms that are quantum safe in the sense that I said before, there are no quantum and no classical algorithms that can crack them as of today. But there's no guarantee that these algorithms cannot be cracked at some point in time by quantum computers. And then they announced we are going to publish these 4 quantum safe algorithms. Right? They announced it, tomorrow we'll publish them, they only mentioned the names. Then they published the next day the name, and 1 hour later a group published an algorithm that cracked one of them. Right? So this means we think there's no proof that they can't be cracked. This is why this PQC task force is an ongoing effort. Every year they release now since 2 years algorithms, because the infrastructure we have to develop has to be agile. Because if one of these algorithms is cracked, you need to unplug it and plug a new algorithm in. Right? This comes later. This is NIST PQC. These are the 4 algorithms that have already been published. This is the next candidate to come, but as I said before, there's no guarantee that they can't be cracked in some future times. Right? This is why we need crypto agility. There's even a document that makes a suggestion how to build agile cryptographic infrastructures. You can download them, read them. Everything is, by the way, completely open. The processes are open. Even the source code of prototypical implementations of the algorithm is open. Right? Here's a layman's view of the architecture. Right? You unplug and cracked algorithm, plug a new algorithm in there, and so on. Right? This is an open, and there is a post-quantum cryptography alliance. There are a lot of industry members here, only a few of them, and what they have, a couple of projects, and the important project is the Open Quantum Safe project. The Open Quantum Safe project publishes a library. The OQS is an open source C library for quantum resistant cryptographic algorithms. All these standardized algorithms are open source, and they even have implementations. They use these algorithm implementations to provide a TLS handshake, to provide certificates that are cryptographically assured, and so on. Everything GitHub repos, lots of contributors, and then the question is typically how to follow the CXO guys. What do I do to become quantum safe? Well, first of all, awareness. That's what I'm, for example, doing, discussing with business leaders, with people from executive boards. And then you need to set up a group to assess the security demand, to protect yourself against harvest now decrypt data, trust or forged data. By the way, what Google has done a year ago, they have a flag. Chrome, by the way, is quantum safe. If you use Chrome to communicate with Google backend, Google Docs, Sheets, and so on, right, there's a flag in Chrome that you can set. It's called PQC. If you set it to PQC, Google Chrome communicates quantum safe with Google backends. Right? And now Safari followed, Firefox followed, and so on. But you need to have a backend that is quantum safe. Right? And Google's backend is also quantum safe. Right? So you need to, this is an organizational hard thing, you need to find out what are the technologies that you use in your company. We are using RSA, ECC, identity signatures, blah, 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 blah. A lot of difficult hard work must happen here. In parallel, people should develop skills in PQC and quantum computing. Many people ask you to found a quantum center of excellence. Could be 2 people or 4 people, right? Quantum center of excellence. But try to find the people. I can give you the name of my staff members. If the first salary goes to me, as usual, right? So, quantum center of excellence. Then you plan and prioritize the transition to PQC and crypto agility, and then you establish security, governance, and migrate. So, now we are closing. There are only very few industry people here, so nobody's really nervous. So takeaways about quantum computing. Quantum is fundamentally different than classical. It's not the same computing paradigm or new machines. It's fundamentally different. You need to understand what unitary matrices are, what complex linear algebra are, very different. This was said before. A new application, new business models are enabled. Powerful quantum computers will be likely available in a couple of years, although with today's machines you can do a lot. Right? We built in a couple of projects that we had with industry partners real-world applications. They are not heavyweight, but you can build real-world applications running productions. The learning curve is quite steep. You can learn it in 1 or 2 semesters, but in order to become very familiar with it, you need more time. Post-quantum cryptography is real act now, and the second takeaway is on post-quantum cryptography is today's crypto infrastructure relies on the hardness of the discrete logarithm problem. Quantum computers will be able to crack the infrastructure midterm, very likely already 29. Lattice-based cryptography seems to be risky, but standards are already rolled out, more under development to enable agility. Open source prototypes of these standards are available, and quantum safe infrastructure must be agile. Time to act is now. Our industry partner here. And the usual final slide that I have in the notes is a quote by Enrico Fermi, another Nobel Prize laureate. Enrico Fermi, Bernard knows, I'm still confused, but at a higher level. I like this statement. So if you enjoyed this talk, the next one will be a bit more mathematical, only a little bit more. So if you want to join, I am happy to. So coffee break. By the way, seriously, short after the talk, all these slides are put online. If you go to the agenda, you will see the videos and slides already for the last days. Yeah. So see you in 15 minutes.